Hey everyone, this is our first part of non-renewable energy resources. So this goes along with the first module in chapter 12 of Friedman and Relaya, and that module is patterns of energy use. All right, so fossil fuels. You guys have been hearing about fossil fuels, non-renewable energy since you were in about the 5th grade. Fossil fuels are derived from biological materials that became fossilized millions of years ago in anaerobic conditions. In the next presentation, we're going to talk about types of fossil fuels and where they came from, but you just need to know that fossil fuels are originally biological that became fossilized. They're non-renewable, which means that they can't be replenished once they're used up. They include coal, oil, natural gas, and nuclear fuel. Nuclear fuel includes uranium and plutonium. Energy is measured in units called joules primarily. We also use BTUs, British thermal units, or quads. Now, quad is a unit that is only used by the United States government to report energy use in the US. So that's a rare one, but you will see it in energy reports if you're looking around on the web. Energy use is not evenly distributed throughout the world. Per capita and per country use varies. Per capita use in the United States is about 5 times greater than the world average. We use a lot of energy in the US to do what we do. 20% of the world's population lives in developed countries, but that 20% uses 70% of the world's energy. So developed countries disproportionately use the world's energy sources. So if we're talking about who uses the most energy, you have to be careful about how you categorize that and what you mean by, quote, the most. So China has the highest total energy consumption per year. But Canada has the highest per capita energy consumption per year. The US is number 2 in per capita energy consumption. Canada's number 1. So the reason that China has the highest total energy consumption is because there's 1.7 billion people in China. But their per capita use is not actually that high. When you take that total energy and you spread it out per person, their per person use is actually fairly low. It's just the fact that they have so many people that they need to supply power to. Canada, on the other hand, has a fairly low population but uses a lot of energy. So when we're talking about per capita energy use, theirs is higher. And again, the US comes in second behind Canada for per capita energy consumption. Commercial energy sources are those that can be bought and sold. These include coal, oil, and natural gas primarily. Less commonly, wood, charcoal, and animal waste. And the wood, charcoal, and animal waste is primarily used as commercial energy sources in developing nations. Subsistence energy sources are those that can be gathered by individuals for their own immediate needs. This includes wood, straw, sticks, and animal dung. So if you're going to go out and build a fire, a cooking fire to cook your family's daily millet porridge, then that's a subsistence energy source. If you're getting an energy source to create electricity or to buy and sell, that's a commercial energy source. Types of energy use generally reflect the level of development of a country. Countries that are developed tend to use mostly commercial energy sources, whereas developing countries rely more heavily on subsistence energy sources. So this is a graph of energy use in the United States. This graph has come up on the AP exam many times. It's basically, and generally they start around 1800. This particular graph starts in 1775. And it goes through 2009. The most recent ones go through about 2015. We do have data through 2015 right now. But you'll get the overall picture by looking at a graph like this. And your textbook also has a graph that I believe starts in 1800 and then goes over again through about 2009. The different colored lines that are right here represent the different energy sources. And this is something that you'll need to be able to analyze on a test. So let's just take a look at petroleum. Petroleum's the red line, and you can see it, it's right there. And it starts generally, petroleum starts generally around about 1875. You start to see it take off closer to 1900, and I'm going to follow it with my pen. It goes like this, and you can see that this is a J curve from about 1925 to about 1950. And then we have some ups and downs here. And we go jig jog, jig jog, jig jog. And on the next slide, we're going to talk about why that jigs and jogs. You can see that natural gas actually follows a similar pattern, although the total amount of natural gas used is lower than the total amount of petroleum. So you need to be able to link historic events in the United States with what is going on this graph. And I'm going to take you through a little bit of that on the next slide. But you can see that we have a huge spike, a J-curve spike in petroleum use, basically through about 1970, from 1900 to 1970. Petroleum and natural gas became kind of the primary energy sources in the United States, primarily oil use there with natural gas to a lesser. Let's take a look at coal. Coal is this one right here, and it's kind of a dark blue. And you can see that coal really starts to take off about 1850. There might be a historical reason for that. I wonder what that could be. Industrial Revolution, maybe? And then you can see that coal takes off. It never had quite the J-curve of petroleum, but it takes off between about 1850 and 1900. And then we get some jig jogs there. We get a dip in 1925 and a spike, and then another dip, and then a higher, right here we get another kind of up and down J-curve. And we'll talk again about why coal has had these ups and downs, and why this, why it's generally up, and in the last few years has kind of taken a fall. Okay, next slide. Okay, so let's take a look at some trends from the previous slide, from that graph, that you could kind of pull out of that. And basically what I did is I just took a look at that graph and I pulled some key dates. So the graph starts in 1775. So between 1775 and 1875, and I might actually even say maybe 1850 here, knowing historically what was going on. That's not clearly shown in the graph, but between 1775 and let's say 1850, wood is our predominant energy source in the United States. We were chopping down forests left and right. The eastern part of the United States was largely deforested, and the reason for that was because we were chopping down trees to burn them as an energy source. Starting, let's say, 1850 to 1875, and this is, of course, during the Industrial Revolution, coal became our predominant energy source. So anything that we needed to do, anything that we needed to power was being run on coal. Trains ran on coal, houses were heated with coal, whatever needed to be done, we were using coal. Beginning in about 1925, oil and natural gas began to gain prominence as fuel sources, and we were actively looking for oil at that time. Think Teapot Dome scandal. Think Spindletop. All those early oil fields. Between 1900 and 1925 that began to come online in the early part of the 20th century. Oil and natural gas, the use greatly increased during World War II, and that was due to the fact that the Navy switched over from using coal-powered steamer ships to oil-powered and diesel-powered very large ships. When we're talking about warships, that's what we're talking about. So once they started abandoning coal, oil and petroleum products kind of came online to fuel those large naval ships. In 1950, electricity from nuclear energy begins to enter the consumer market. Now, the technology for nuclear energy was developed, of course, during World War II, and we actually began, using nuclear power to fuel primarily submarines and some battleships during World War II. But in the 1950s, we used that same nuclear fission technology to start to bring nuclear power plants online to provide non-military energy. So as I mentioned in the previous slide, in the 1970s, we see a dip. We see a dip in oil and natural gas consumption. Well, why was that? There was largely socio-political stuff going on, and that was the OPEC embargoes. And the U.S. was not getting shipments from the Middle East, from OPEC countries, for oil and gas. So we were developing domestic resources of those, but because domestically we weren't supplying as much as we had been importing, our usage dipped at that point. And anyone who was alive during the 1970s can tell you we had a lot of austerity programs about making sure that we were using energy efficiently, turning off lights, because we were in an energy crisis during the 70s. US coal at that time resurged as a fuel source because, again, we were not importing oil from OPEC nations at that point. Post 1985, oil and natural gas have become the predominant US energy sources. Coal is third, and it's primarily used for electricity generation. We are not heating our homes with coal anymore. We are now using coal primarily as an electrical generation source, and we'll talk about that later. Today, in today's world, natural gas consumption is increasing due to fracking. Fracking technology, which we will talk about again in a different presentation, has allowed natural gas to become more plentiful and to be able to be transported to different markets more easily. So natural gas consumption is currently increasing, and the use of renewables also, especially wind power, is also increasing and has greatly increased since 2000. And you can see that in the graph on the previous slide as well. So right now, the energy mix in the United States is about 81% fossil fuels, 9% nuclear, and 10% renewables. And I'm going to show you a graph on that in the next slide. There you go. So this is from 2015. And frankly, 2015, 2016 is the most recent data that we have for a lot of our energy consumption graphs. So, and your textbook is a little bit out of date. I think that they stopped their analysis in 2009. So the graphs that are in this presentation are updated with newer information. U.S. energy consumption by source in 2015, and this goes along with what I just told you. If you look, I don't know if you remember me talking about the quad a couple of slides ago, but see that right there, the word quadrillion, that's where the word quad comes from, and this is how the U.S. actually reports its energy use is in these quads. You'll see that in your book as well. They talk about what a quad is equal to. You don't have to memorize what quads are equal to. Just know that the U.S. reports its energy use in quads, which is a BTU equivalent, and you can actually see that here on this graph. All right, so we've got petroleum at 36, natural gas at 29, and coal at 16. If you add 16, 29, and 36, you get 81%. Nuclear power is about 9%, which is a little bit higher than it shows in your textbook, and renewable is also at 10%. So that's where we get our energy consumption by source for the U.S. Okay, so forms of energy are suited for specific purposes. This makes sense if you think about it. You're not going to run a car by burning wood. There's obvious reasons why you wouldn't, right? So let's talk a little bit about this. The best form of energy to use depends on the job that you need to get done. Energy to mass ratio is important to consider. So let's talk about transportation, which was my example, right? In transportation, liquid fuel like gasoline or diesel is preferred. Why? Well, because liquid fuel allows you to travel much farther with a smaller mass of fuel to transport than energy sources such as wood or coal. If you were trying to fire your car on wood or coal, you would have to take a lot of that fuel source with you in order to go a distance. Liquid fuel like gasoline or diesel is much more concentrated, so the energy to mass ratio is better. Put it in your tank, you can go a lot farther than you would on the same amount of wood. In addition, gasoline and diesel can begin and end combustion quickly. I mean, you can turn combustion for gas on and off. That's what you're doing when you hit the ignition, right? You're beginning combustion. Wood and coal, on the other hand, you have to stoke a fire in order to do that. I mean, think about the steam trains, right, of the 19th century. They were run on coal. You had a big, huge boiler in the front. The boiler, that's the steam train. The coal was firing the boiler that powered the steam, that powered the pistons that ran the train. And that was a long process. Those steamers had to warm up, right? You had to get the water to boiling, and then the steam had to be kept at a boiling point. So for transportation, obviously, gasoline and diesel are much more efficient than wood or coal. So energy efficiency refers to the efficiency of the process we use to obtain the fuel and the efficiency of the process that converts it into the work that's needed. So different energy sources have different energy efficiencies. Energy efficiency is governed by the second law of thermodynamics, which says that when energy is transformed, its ability to do work diminishes because during each transformation, energy is lost. And they go on about that in your chapter. You should already know about the second law of thermodynamics because everybody took physics. We're going to talk about EROEI, which is energy return on energy investment. this is an equation which is a direct way to account for how much energy it takes to produce a given fuel source. If that doesn't make sense, it will on the next slide. Anytime we have a fuel source, it takes energy to produce a fuel source. Let's take coal, for example. Coal has to be mined out of the ground, right? It doesn't just pop up out of the ground naturally and you walk by and grab a chunk of coal. It has to be dug out of the ground. Well, that digging process and that transportation process to the coal-fired power plant or whatever you're going to use it for, that takes energy. So it takes energy to produce a fuel source. And different fuel sources have either a higher or lower EROEI based on how much energy it takes to obtain them. So let's take a look at that mathematically. All right, so here's a graph on energy return on energy invested. This is the EROEI equation. I have never seen that people have to calculate this on the exam, but you do have to know the concept of it, and it's fair game for them to give you a graph that looks like this. Sometimes this graph is referred to as the net energy cliff, and the reason why is that it's usually shown with just this blue line right here, which is this, and you can see it kind of resembles a cliff. What they're talking about here, so the blue line is the energy return, and the red line, which is the inverse, is the energy invested, and that makes sense. So the energy return, as the energy return goes down, the energy invested goes up, and they should be inverse of each other. The green line here is energy produced, and that is, of course, is set to 1.0 or 100% on this graph. So along here, you can see also that the x-axis here goes to 30, which is the energy, which is the scale here. Now, coal is off this scale. It would be over here on the left, as is hydroelectric. And hydroelectric is set to 100. Let's talk a little bit about hydroelectricity in 100. And of course, this is not a PowerPoint on renewables yet, and we will talk more about that. Once a hydroelectric power plant is built, there is no additional energy input. Now, during the building process, of course, there's energy input, and hydroelectric plants are expensive to build. However, they're using a fuel source, moving water, that would move on its own. So when we're talking about energy input, once the plant is built, there is no additional energy input. That energy is already there. So that is set to 100. Different energy sources along this net energy cliff or this curve have different EROEIs. So again, down here is the equation. That's the energy delivered by the fuel source divided by the energy required to deliver that fuel source. So domestic oil is listed here, wind, nuclear, imported oil, natural gas, solar photovoltaics, shale oil, tar sands, solar thermal, which is, we haven't talked again about renewables yet, but this different way to generate solar electricity. And then ethanol is down here. Your book makes a big deal about ethanol. There is a applied science module that we'll be doing about should corn be turned into ethanol. If you ever fill up a vehicle with gas, you will see that on the gas pump here in the Dallas area, it says this fuel contains 10% ethanol. That ethanol is produced from corn, which, as you know, we have a lot of in the United States. So the question is, what is the EROEI of turning corn into ethanol? You can see right here, it's really, really low. There's a lot of energy put into the process of creating corn into ethanol, and it's not a great return on investment. And we'll get more into that later. Okay, so let's talk about transportation. Transportation accounts for about 30% of U.S. energy use. Most vehicles run on gasoline or diesel. So we're going to discount hybrid electric and fully electric vehicles because most of them, 99% of them, run on gasoline or diesel fuel. Transportation efficiency depends on how many people the vehicle can transport versus the amount of fuel used by vehicle. So, for instance, if we're talking about, let's say, a bus. Buses very much use more fuel than a passenger car. However, buses usually have more people on them than passenger cars as well. So efficiency depends on the number of people that can be transported versus how much fuel the vehicle uses. So in this particular way of calculating efficiency, trains and motorcycles are our most efficient vehicles. Trains, passenger trains, because they carry a lot of people versus their amount of energy use. Now they're diesel powered. And motorcycles are very efficient. They're only transporting one person, but they don't use very much energy. So motorcycles tend to be a very efficient way to transport yourself. Now, if all 4-passenger cars in the US actually carried 4 passengers, then cars would be a more efficient means of transportation. But a full car, a passenger car with 4 people in it, is a rarity in the United States. Most passenger vehicles have 1, maybe 2 people in them. So that makes them less efficient because they're using a fair amount of fuel to only transport 1 person. Efficiency ratings do not take into account personal convenience, they don't take into account comfort, and they certainly don't take into account style. So many Americans choose to drive personal vehicles that have low fuel efficiency due to a combination of these factors. If you want to talk about convenience, efficiency, convenience, comfort, or style, taking the bus ain't it, guys. But you have to say, like, when you're talking about just straight up efficiency, how much does that matter, and does that factor into it? Our current way of calculating efficiency doesn't take that into account, but obviously when we're talking about personal opinion, those are some big factors. There's a graph right down here that shows average estimated fuel economy by model year for US cars, trucks, and then both of them. Since 1990, more people have chosen to drive SUVs and light trucks. Those vehicles are less fuel efficient than passenger cars. They get fewer miles per gallon. So you can see here that the trucks, which would include SUVs as well, SUVs and light trucks, those are lower on the average mile per gallon scale than cars are. But check this out. Since about 1980, guys, we have not had a large boost in fuel efficiency. See that flat line? Now, starting in, this one goes to 2010, so that's the end of the graph. This is about 2000, this is between 5 and 10. So between 2005 and 2010, we actually had an increase in fuel efficiency for all of our passenger vehicles in the US. And that was largely driven by legislation. So we passed laws that said fleet efficiency in the US had to increase, and vehicle manufacturers responded to that. Do we have the technological capability to make cars and trucks more efficient? Oh my gosh, yes. Cars and trucks could be made a lot more efficient than we currently make of them, but the demand isn't there in the United States. If you go to Australia, if you go to New Zealand, if you go to Europe, cars and trucks are much more fuel efficient than they are here. The technology is available. The issue is that in the US, gas prices are so much lower than they are throughout the rest of the world that we just we're not driving the demand for the increase in that technology. So car manufacturers respond to consumer demand. Since the demand's not there, they do not increase their technology for fuel efficiency. They only increase it when laws make them do that, and that's the legislative input part. So let's talk about electricity. Electrical generation accounts for about 40% of US energy use. Electricity can be generated from many different fuel sources. You can make electricity from fossil fuels, from nuclear fuel, from biomass, from wind, water, solar, and geothermal energy. Electricity is considered a secondary energy source. That means that we obtain it by conversion from a primary source. So these up here are our primary sources. And then electricity is our secondary source that is generated from one of these primary sources, or more than one of these primary sources. This also means that electricity is an energy carrier, which is something that can move and deliver energy in a convenient, usable form to end users, to consumers. The efficiency of electrical generation depends on the fuel source that is used and the cumulative conversion losses from the source of the energy, which is the power plant, to the end user. On average, transfer of energy from a fuel source to an end user is only about 35% efficient in the United States. That should say fuel source. From a fuel, it should say fuel source. Okay. Electricity is clean at the end user standpoint. That is, as you're sitting in your house, plugging in your cell phone or using your microwave or whatever you're using electricity for, no pollution is being emitted by that electrical outlet. The pollution that electricity produces is caused by the fuel source that's used to generate it. Regardless of which type of fuel is used, however, all power plants work in the same way. They convert the potential energy of a fuel into electricity. So 2 graphs, sources of electrical generation or generated electricity in 2012 versus 2016. And this is kind of important because for many, many, many years, coal was the #1 fuel source that was used to generate electricity in the United States. Now, the burning of coal has a lot of drawbacks. It's got some positives too, but it's got some drawbacks. So let's look here, down here. We're down here right now. I'm going to talk to you about what I put down here, and then we're going to talk about pros and cons. So until 2016, coal was the primary fuel source for electricity generation in the U.S. But as fracking has increased and the availability of natural gas has increased, natural gas is now the #1 fuel source in the United States for electrical generation, and that started in 2016. In 2015, they were almost neck and neck, but in 2016, natural gas edged out coal. So there's pros and cons to this, as there are for all the different fuel sources that are used to create electricity. You guys, coal is a dirty energy source. When you burn it, stuff happens. There's particulates that come out from the burning of coal. There's sulfur dioxide and sulfur monoxide, primarily sulfur dioxide, which combines with water vapor in the air to create sulfuric acid, which creates acidic precipitation. That's a bad thing. That's a negative. When coal is burned, heavy metals are released, mercury primarily. So downwind of coal-fired power plants, we often have mercury contamination in both the soil and the water. That's obviously a bad thing. Mercury contamination is a negative. So there's a lot of reasons why you might want to move away from coal. Now, one of the reasons you might not want to move away from coal is because the U.S. has a lot of coal. The U.S. is got a lot of proven reserves of coal. At our current rate of coal usage, those reserves will last us in excess of 300 years. So if we're talking about keeping our energy sources domestic, coal's a great choice. If we're talking about environmental consequences, coal's not so great a choice. So moving to natural gas. Natural gas is a much cleaner burning fuel. Natural gas does not produce particulates when it is burned. It produces about half of the carbon content of coal when it is burned. Now, is it still a fossil fuel? Yes. Does it still create carbon dioxide? Yes, which of course is a greenhouse gas. But it doesn't create particulates, which have their own negatives, and we'll talk about that when we talk about air pollution. And it creates less carbon dioxide pollution. On the other hand, the process used to obtain natural gas, which is at this point largely fracking, when fracking is done, and we'll talk more about fracking as well, but when fracking is done, we release other greenhouse gases such as methane and hydrogen sulfide, which exacerbate global warming. Fracking has some other downsides, and again, we'll get more into those. So when we're talking about actually just burning natural gas, it's more efficient. We're going to talk about when you burn it, when you actually create electricity from natural gas, it is much more efficient than coal. It's cleaner burning than coal. But the process used to extract it is also environmentally damaging and in different ways than the extraction of coal is. So there's pros and cons for every single fuel source on this list. And of course, we'll go through all of those. But in terms of how we generate electricity, we've moved from coal primarily to natural gas. Our majority is now natural gas. All right, so let's talk about how coal-fired power plants work. I'm going to go through this slide. The graphic for this is on the next slide. So you might want to write some of this down and then take those notes and kind of compare them against the slide that's coming up. So coal is delivered to a boiler where the coal is burned. The heat from the coal fire transfers energy to a body of water. There's a tank there, and that water turns into steam. The kinetic energy from the steam is transferred to the blades of a turbine. A turbine is a device with blades that can be turned by steam, by water, or by wind. As the energy from the steam turns the turbine, there's a shaft in the center of the turbine that is connected to a generator, and that the turbine spins, it turns the shaft, and the shaft powers a generator, which generates electricity. The electricity is transported along a network of interconnected transmission lines, and that is known as the electrical grid. The grid connects power plants to each other, and it also connects the power plants to the end user grid. That should be actually a vocabulary word, and that should be bolded right there. After the steam passes through the turbine, the steam is cooled and it's condensed back down into water. The water can be cooled. This condensation can happen in a cooling tower, which is exactly what it sounds like. It's a big, huge tower that has these fins on the inside, almost like what you see on a air conditioning unit. They run the water down the fins, and that increased surface area cools it down. Or the warm water can be discharged into a nearby body of water. Most coal-fired power plants in the U.S. are located by a body of water so that the hot water can go back into that water. If the warm water is discharged into a body of water, then thermal pollution can become an issue. So here's the schematic that talks about the steps that we just talked about. So in this particular schematic, the power plant is by a river, which is used as the place where the water is cooled down. The condenser cooling water goes back into the river. And so you can see the different steps here. The coal is delivered to the boiler, where it is heated, where it is burned to heat water that creates steam. The steam flows up out of here. The steam turns the turbine, which is this thing right here. You can see the shaft that goes through the middle. That shaft is turning. This is the generator. So the shaft turns the generator, and the generator creates the electricity. The generator is connected to the transmission lines. They go through a transformer to change the energy from one form to another, and you don't really need to know a lot about that. And then the transmission lines go out to the grid that connects power plant to power plant and power plant to end user. So here's the water right here. You can see that there's a condenser right down here, which is where the water goes after it's converted into steam. The steam comes through here and it's condensed, and then it is dumped back into the river. And the river, of course, in this, the river, of course, in this case is both the source and the sink where the water is put back into. When you are putting warm water into a body of water that's not normally that temperature, we get what we call thermal pollution. Thermal pollution has some consequences. When you increase the temperature of water, you decrease its ability to hold oxygen, so you decrease its dissolved oxygen levels. You can increase the growth of algae and bacteria. You can also thermally shock fish, so you're changing the species composition, because certain fish are not going to be able to live in, or certain aquatic organisms will not be able to live in the warmer river water. So you have a species shift. Sometimes here in Texas, actually, we actually stock game fish in waters that we thermally pollute, so that people can go and fish for fish that wouldn't normally be in those rivers or those bodies of water, because they can't tolerate the warmer water. Legacy coal-fired power plants have an average efficiency of about 35%. When I say the word legacy, I'm moving the slide. When I say the word legacy, I'm talking about the older coal-fired power plants, ones that were built, 50, 70 years ago. Coal-fired power plants are still being built, and the newer coal-fired power plants are usually more efficient than that 35%. And that's just because technology has improved. Natural gas-fired power plants that run on natural gas, like what we talked about before, are almost twice as efficient, about 60%, as coal plants. And this is due to what we call combined cycle technology. Many of these natural gas plants, they burn the natural gas, and the combustion products are used to turn a gas turbine. This gas turbine is not using steam. It's using the combustion products of the natural gas. These turbines look a lot like a jet engine, actually. They're pretty cool. So the waste heat from that combustion is then used to boil water, and the steam turns a conventional steam turbine. So you actually have two different ways to generate heat in a natural gas-fired power plant. So again, Because there's two different ways to do that, and it's fired from the same fuel source, that means that that fuel source is more efficient because it's generating electricity in two different ways in the same plant. The capacity of a power plant is its maximum electrical output at any given time. This is typically around 500 megawatts. You multiply the capacity by the amount of time in a 24-hour period that the plant is in operation to get the plant's daily electrical output. Generally, when we're doing this energy math, we assume a plant is online 24 hours a day. But, sometimes they're not. Sometimes they go offline, or they have reduced capacity at certain times during the 24-hour cycle. The capacity factor is the fraction of time a power plant operates in a year. For coal-fired power plants, this is usually around 90% or 0.9. Nuclear and coal-fired power plants remain in nearly constant operation because it takes these plants almost 24 hours to become operational once they're shut down. So if you shut down a nuclear or a coal-fired plant, there's kind of a startup process or a warm-up process that they have to go through, and that takes almost 24 hours for them to come back online. So you really don't shut them down that much. Now you can shut down certain parts of them, so maybe only one reactor is going, or maybe only in coal-fired, maybe only one or two furnaces are powering at a time. So they're reducing their capacity, but they never really go totally offline. Natural gas-fired power plants, on the other hand, can be turned on and off easily because there's almost no warm-up time, which makes them a better choice for fluctuating electricity demand. Cogeneration is the use of a fuel to generate electricity and produce heat. This is also called combined heat and power. This has been tested multiple times on the exam, so it's definitely something that you need to know. This is generally used with steam technologies. The steam is first used to turn a turbine, which generates electricity. Then the steam, which is still very hot, is diverted for industrial purposes or to heat buildings. So when we're talking about, think back to the coal-fired power plant schematic, that steam, rather than being condensed and put into a body of water or reused, what they do is they use that steam to create heat for an industrial process or to heat buildings. The efficiency of cogeneration is actually very high. It can be up to 90% efficient, which is good because you're using one fuel source to do two different things. All right, so let's talk a little bit about energy math. This is a math problem that was shown in the end of this particular module in your textbook, and I'd like to go through it with you. This is the kind of math that you'll be expected to do on the exam. So according to the U.S. Department of Energy, a typical home in the U.S. uses about 900 kilowatt hours of electricity per month. There it is right there. How much energy does a typical home use in a year? All right, well, to figure that out, you take your 900 kilowatt hours per month and you multiply that by how many months are in a year. Okay, the months cancel out and you end up with 10,800 kilowatt hours per year, and that's per home. So how many homes can a 500 megawatt power plant with a 0.9 capacity factor support? Okay, well, first we got to figure out per month how much can it support. All right, so we've got our 500 megawatts. That's our capacity, right there. And we're going to assume that it operates 24 hours a day. We're also going to assume, on average, that months have 30 days. Okay, so you can already see that our days are going to cancel out right there. Okay, and then we're going to multiply that by our capacity factor, which is 0.9. So we've got 500 megawatts times 24 hours per day times 30 days in a month. So we're left with months as our unit, times our capacity factor, which gives us 324,000 megawatt hours per month. But we need to convert our megawatts into kilowatts because for homes, we use the kilowatt as a measurement rather than megawatts. So we're going to convert our megawatts to kilowatts. So 324,000 megawatts per hour per month. Right? That's what we got from up here. And then we have to multiply that by 1,000 because there are 1,000 kilowatts in a megawatt. 1,000 kilowatt hours per megawatt hour, right? And so this is going to cancel out, and we're going to get kilowatt hours per month. And that's 324 million kilowatt hours per month. Now we have to find the number of homes. So we take our number here, 324 million kilowatt hours per month, right down there. And we divide that by the 900 that they gave us up here, 900 kilowatt hours per month per home. And we come up with 360,000 homes that this power plant can support. So on average, a 500 megawatt power plant with a 0.9 capacity factor can supply 360,000 homes with electricity. Bing! Okay, so we're going to expand on the math that we did in our previous problem and talk about what happens when we increase our energy use. So during the summer months in hot regions of the US, some homes run air conditioners continuously. That would be Dallas in the summer because it's 1,000,000 degrees. However, so how many homes can the same power plant from the previous example support if the average electricity usage increases to 1,200 kilowatt hours per month during the summer months? All right, so let's just take our numbers from our previous problem. So we had 300, oops, I'm moving the slide again. Y'all, I'm so bad with that. 324 million, that's a lot of zeros, kilowatt hours per month. I'm just going to put MUN, okay? And we had to divide that by 900, which was our average kilowatts per month per home, okay? Kilowatt hours per month per home, right? And we ended up with 360 homes that could be powered by that power plant. Okay, everybody with me? That's from the previous problem. But now this 900 is going to increase to 1,200. So we're going to take 324 million. That's 324 million, Bagley. Kilowatt hours. And notice, guys, that I'm writing out my units. That is required. You have to do it. It's a pain in the rear end, but you're going to have to do it and get used to it, okay? So write it out. No matter how much of a pain it is, write it out. I want you to get credit when you do your math. Okay, now we're going to divide that by 1,200 kilowatt hours per month per home. And when we do that math, that comes out to 270,000 homes. That's a 7, not a, I don't even know what that was. That's a 7, 270,000 homes, okay? So what's the difference between 360 and 270,000? Well, show your dang math. 360,000 minus 270,000 is a difference of 90,000 homes. So the answer to this question, how many fewer homes can the same power plant power during the summer months? 90,000 fewer homes. Now, I'm assuming that the summer months are June, July, and August. It doesn't say, does it? But this is what I'm going to assume. So in June, July, and August, that same power plant can only power 270,000 homes because the energy usage has increased. That is a decrease of 90,000 homes fewer. So the question is, what's going to have to happen if that same power plant, which supplies 500 kilowatt hours, 500 megawatts at its capacity, what's going to have to happen when we have increased energy usage? Well, we have to have a backup power plant that comes online during the summer months to help supply that energy gap there. Everybody got it? Hopefully that wasn't too terrible. Okay, thanks guys. Stay tuned for the next installment. Bye.